In our previous lecture, we discovered the relation between the impedance of a passive one port that does not contain any independent sources and certain physical quantities. Physical quantities such as the powers dissipated throughout the resistors within the one port, and also the total stored energies, average stored energies in the capacitors and inductors within the one port. Okay, so more precisely, what we have found was that the real part of the impedance was proportional to the total average powers dissipated throughout the resistors within the one port, and the imaginary part, or the reactance of the impedance, was proportional to the difference of stored average stored energies in the inductors and the capacitors, and the proportionality constant was the square of the effective value of the current that's visiting the one port. In this hour, we will put all those results in a more formal setting by introducing the so-called complex power for a one port. Okay. So suppose that this box represents our one port that's part of a LTI circuit that's in sinusoidal steady state. Okay, so let's name it N, and this circuit, or this one port, is in sinusoidal steady state. Okay, all the currents and voltages are oscillating at the same frequency, omega. So this indicates the voltage, and I indicates the current of our one port. Now, for this one port, we define the complex power as follows. The complex power delivered to the one port N is defined as follows. Okay, so usually it's indicated by capital S, and the definition is 1/2, and then the product of the phasor of the voltage V and the conjugate of the phasor of the current I. Okay, so it's 1/2 V times I star. Remember that this star notation simply means that complex conjugation. Okay. So this is how we define the complex power. At this point, it may seem just an arbitrary mathematical definition, but it will prove very useful when we start looking at the complex power from the physical point of view, namely from the point of view of powers and stored energies. Okay, where V and I are the phasors of V of t and I of t, respectively. Okay, now let us write the voltage phasor in polar coordinates, which equals some positive real number, namely the magnitude of the phasor, times e to the j times some phase, and that phase is the phase of the voltage. Likewise, the current can be written as some magnitude e to the j times the phase of the current phi I. Okay. Now let's put these expressions into the definition we have just introduced. That yields what? S equals 1/2 Vm Im times e to the j phi v times, because of this conjugation, we have e to the minus j phi I. Okay, and that can be written as a single exponent, e to the j phi v minus phi I. Okay, So this is the polar representation or expression of S in polar coordinates. This is its magnitude, 1/2 Vm/Im, and the phase is the difference of the phases of voltage and current, phi V minus phi I. So that can be written in rectangular form as follows: 1/2 Vm/Im, so that's the magnitude, times, because e to the j theta is cosine theta plus j sine theta, the famous Euler's identity. This can be written as cosine phi V minus phi I, so that's the real part, plus j 1/2 Vm/Im, and then the sine of the phase difference, phi V minus phi I. Okay, and that equals, remember that for a sinusoidal signal, okay, the effective value is the amplitude divided by square root of 2. Therefore, this 1/2 Vm/Im can be written as V effective times I effective, or Vrms times I RMS. So let's do that like that. Vrms times I RMS cosine phi V minus phi I plus j RMS I RMS sine phi V minus the phase of the current, phi I. Okay. Now, we remember from the previous lecture that, note that the real part, okay, of the complex power is Vrms IRMS times the cosine of the phase difference between voltage and current. And that was the average, that was the power, average power associated to the one port. And if one port is passive, okay, without any independent sources, that would be the average power consumed by that one port, okay, or delivered to the one port. So this equals V RMS I RMS cosine phi V minus phi I. And that's, for a passive one port, was the average power delivered to one port N. Okay. For that reason, from now on, we will be indicating the real part of S by P. And we have the following further subdefinitions. Okay. First of all, S is defined as the so-called complex power. It's a complex number, but it's not a phasor, okay? Because it's not representing some time domain signal, okay? So that's our complex power. This is not a phasor, okay? Just a complex number. And then P, okay. So average power delivered to N. So what we do is, hence we write, hence we write from now on S equals P plus JQ. Okay, so when we write the complex power in rectangular form, we're going to indicate the real part by P, motivated by that observation, and the imaginary part by Q. Now S is the complex power, P is the real power, okay, sometimes called active power. And this is measured in watts. Okay. So, in other words, P is the real part. P corresponding to a one port. One port is the real part of this complex number, 1/2 V times I star, or the real part of S, and that equals V RMS I RMS times cosine phi V minus phi I. Okay, now The imaginary part of the complex power, which is labeled Q in general, is called reactive power. Okay, and this is measured in volt, ampere, and reactive. Okay, the abbreviation for that unit is capital VAR. VAR. And Q is, by definition, the imaginary part of the complex power, S. And that equals VRMS, IRMS. Note that this is the magnitude of our complex number, which will also have a name soon enough. Okay, magnitude times the sine of the phase difference, phi V minus phi I. And finally, let's also give a name to the magnitude of the complex power. Okay, the magnitude of the complex power is called apparent power. And measured in volt ampere, okay, without the reactive. So what we do is we write VA. Now, volt times amps is watts. So this seems like this W and this VA, the same thing. But for communication purposes, we never write watt for this or volt times amp for that. Because when we express something and give the proper units, that unit will tell us what we're talking about, okay? If you're talking about a load with 1000 volt amp, okay, or load at 1000 volt amp, we're talking about the apparent power. If you're talking about load at 1000 watts, so we're talking about certain load where the real power or the active power is 1000, okay, volt watts. And S, the apparent power, is 1/2 VMIM, okay, the magnitude, product of magnitudes of voltage and current, and you divide that by 2, or simply take the product of the effective values of voltage and current. VRMS, IRMS. Or if you know separately P, okay, and Q, active and reactive powers, then it's simply the length of the hypotenuse, okay, if you consider P and Q as the right sides of the triangle, the right triangle. Okay. Now this, let's apply now this definition, the complex power, to a one port that does not contain any independent sources and all the components inside are passive. Therefore, we can represent this by an impedance Z. And then we will be able to figure out the relation between the complex power and the impedance of our circuit. Okay, now consider now a one port containing possibly ideal transformers and passive resistors, inductors, and capacitors only. So we have no sources inside, independent or dependent. Such a one port can be represented by its impedance from the point of view of input current voltage characteristics. Okay, so let Z indicate its impedance, and here we have the voltage, and this is the current in phasor domain. So what we have is V is, as before, the magnitude and then phi V, e to the j phi V, and the current phasor is the magnitude times e to the j times the phase of the current, phi I. Okay. Therefore, we can write Z equals, okay, by definition, it's the ratio of the voltage phasor to current phasor. So that allows us to write Vm over Im, and then e to the j phi V divided by e to the j phi I, that can be written as a single exponent, e to the j phi V minus phi I. Okay. And this here magnitude, and that's the magnitude of our impedance, therefore that can be written as the magnitude of the impedance times e to the j phi V minus phi I. Okay, and remember our previous notation. The real part of the impedance is denoted by R, and sometimes called the resistance of this one port, and the imaginary part is denoted by X, sometimes denoted by sometimes called the reactance of the one port, R plus JX. Okay, now let's try to make the connection between Z, or R and X in particular, and these things that we have just recently defined, complex power S and P and Q, its real and imaginary components. So, what's the complex power associated to this one port? Okay, so that's the question we will easily answer now. What's the complex power for our one port whose impedance is Z? Let's apply the definition, which is V times I star, and that's 1/2. What's V? V is the impedance times the current. And then we have I star. Note that I times I star will give us the magnitude of the current square. So we can write this as 1/2 Z I m squared, the magnitude of the current square. And we can get rid of this factor 1/2 by expressing this in terms of the effective value of the current, or the RMS value of the current. They are the same thing, which is the magnitude divided by square root of 2 for a sinusoidal signal, and we're dealing with the sinusoidal case here. Zi RMS square. Okay, therefore the complex power is, for a one port, for a passive one port, is proportional to the impedance, and the proportionality constant is the square of the effective value of the current. If you express complex power in terms of the effective value of the voltage, then you would have S equals V RMS square divided by not Z, but Z conjugate, okay, which directly follows from the definition. Okay, so so S equals impedance times the RMS value of the current square, and that equals also RI RMS square plus J XI RMS square, because Z, okay, in rectangular form can be written as R plus JX. We also know that S equals P plus JQ, P plus JQ, and that puts everything in a clear way, namely the relation between S, P and Q and Z, R and X are now clear. So P, the real power, is the real part of the impedance multiplied by the square of the effective value of the current, and Q is the reactance times the square of the IRMS. Okay, so let's therefore make or put those relations clearly down. So this is the simple relation between SPQ and ZRX. P is the real part of Z times IRMS square. Okay, IRMS is the effective value of the current passing through our load or one port, and that equals R times IRMS square. And this is the real power delivered to our one port. Q is the imaginary part of the impedance times IRMS square. That's the reactance times IRMS square, which is the reactive power. Okay. Note that this reactive power was proportional to the difference between the total stored energies throughout, average stored energies throughout inductors within our one port, and the average stored energies throughout the capacitors. And finally, the magnitude or the apparent power is the magnitude of the impedance times IRMS square. That's R square plus X square times IRMS square. And this is the apparent power, okay, associated to our one port. Okay, real power measured in watts, reactive power measured in volt amp, reactive var, and apparent power is measured in volt amps, VA. Okay, now to indicate or to communicate what part of the apparent power is going to the real power, we will now introduce a new object, namely the power factor, okay, associated to the one port. So the power factor is defined as the ratio of the ratio of the real power to apparent power. In other words, okay, it's not on the board. In other words, it's the cosine of this phase difference between voltage and current. So power factor, indicated by lowercase letters PF generally, is cosine phi v minus cosine phi I. Okay, so once again, the power factor for a one port is the cosine of the phase difference between the phase of the voltage and the phase of the current. Okay, so since it's cosine of something, it can at most take the value 1. Okay, and magnitude wise, the smallest that it can get is 0. Okay, note that we can write Z as the magnitude times the power factor plus J magnitude times sine phi v minus phi I. This is right, that's the sign of the phase difference phi v minus phi I. And likewise, S can be written as pjq. And the real part is the magnitude times the same scalar, the power factor, cosine phi v minus phi I, plus j, the magnitude, sine phi v minus phi I. Okay, and so that's the complex power. Now, let theta be defined as that phase difference phi v minus phi I, and then sometimes those two complex numbers are, for communication purposes, are represented as right triangles. And since the phase of these two numbers, complex numbers, are the same, namely phi v minus phi I, when these are represented by right triangles, those triangles will be similar. Okay, not surprisingly. So here is the triangle representation of the complex power. Sometimes it's called the power triangle. Okay, this is our theta. And the horizontal side is P, the hypotenuse is the apparent power, and the remaining side represents the reactive power. Okay, and we would have the similar triangle for the impedance, where the hypotenuse will be the magnitude of the impedance. Here we have the same angle theta, which is phi v minus phi I. This is the resistance, and here we have the reactance corresponding to our impedance. Okay. Now, depending on the range that theta, or phi v minus phi I, belongs to, the one port is classified into different types. Okay, we already talked about that. Now let's re-talk about it, having introduced the complex power. Okay, we will have 5 cases that we want to name. So we're studying now a one port that's passive, contains no independent sources, therefore it can be represented by an impedance, and the real part is denoted by R and the imaginary part denoted by X. Okay, in polar coordinates it's written as e to the j theta, and theta equals the phase difference between phi v and phi I. Phi v, phi I being the phases of the voltage and the current of, or at the port terminals for our one port. Okay, so case 1, theta equals 0. Okay, so when theta equals 0, remember that this is our theta. Power factor is as large as possible, namely power factor is 1. In that case, one port is said to be resistive. Okay, so R is positive. The imaginary part of the impedance is 0, so the reactance is 0, and the power factor, which is cosine theta, equals the largest value that it can take, namely 1. As for the powers, the active power, or the real power, or the average power, it's positive. Reactive power is 0. This is the imaginary part of our complex power. So we have 0 reactive power. Hence, the apparent power, magnitude-wise, equals the average power. Okay. Now, that one port is resistive. Does not mean that inside our circuit we have only LTI passive resistors. Okay. It just means that neither inductors dominate over capacitors, nor capacitors dominate over inductors. Okay. So the stored energies in the inductors, total stored energy, average stored energy in inductors, equals the total stored energies, average stored energies in the capacitors, okay? And that would produce a 0 reactive power, okay? So that means, right, in that case we call the one port resistive. Of course, this thing, since Z depends on the frequency, therefore its real and imaginary part depend on the frequency. At a different frequency, okay, it may not be resistive. This condition may break down. So that we should always keep in mind that all these conclusions that we make are considering some particular frequency. Okay, let's say 50 Hertz, the usual frequency of the network. Okay, so that's the largest power factor case. Then we have the following situation: theta between 0 and 90 degrees. Okay, in that case, one port is said to be inductive. Okay, and such one port is said to have lagging power factor. Okay. Why lagging? Because the current of at the port terminal is lagging the voltage at the port terminal. Current lags voltage. So we have R positive, X also positive. Okay, why? Because this is somewhere between 0 and 90, and sign of such a phase is positive. Okay, therefore we have positive reactance. And PF is somewhere between 0 and 1, and it's said to be a lagging power factor, because if you only know the power factor, since cosine of phi v minus phi I and cosine of phi I minus phi v is the same, cosine is an even function, you cannot determine by just knowing the power factor the sign of the phase. So when the power factor is given with this expression, lagging or leading, we will be able to determine also the sign of this phase angle. Okay, and in this case the power triangle is drawn in this way. S, this is theta, this is P, and this is Q. We have just 3 other cases. Case 3, theta between minus 90 degrees and 0. In this case, one port is said to be capacitive. Okay, so R is positive. This time X is negative, the reactance, and the power factor is said to be leading. Okay. And P is positive, the reactive power is negative. Okay. Now, since for the first case, which we call resistive one-port case, this does not mean that one port does not contains only LTI resistors. Similarly, when one port is said to be inductive, it doesn't mean that we have only inductors inside. Okay. Or when one port is said to be capacitive, it doesn't mean that we have capacitors only inside. It just means that inductors are dominating the capacitors. And by dominating, we mean the total average stored energies in the inductors is larger than the total stored energies in the capacitors. And here we have the dual case. Okay, capacitors are dominating inductors. And for this case, the power triangle is drawn in this way. Okay, so this side now pointing down in a sense, just to indicate that we're talking about a negative reactive power. Okay, this is P, here we have Q, a negative number, and this is our theta. And here we have the apparent power, the hypotenuse. And the remaining two cases, cases 4 and 5, are the extreme cases. One is that theta equals pi over 2, where one port is purely inductive. Okay. Namely, R equals 0. The real part of the impedance is 0. The reactance is positive, and the power factor is magnitude-wise as small as possible. PF equals 0. And we write here also lagging to indicate that we're at 90 degrees, because cosine of minus 90 also produces 0. So to figure out whether, or to communicate whether this is given by plus 90 or minus 90, we put either lagging or leading respectively. Okay, P equals 0, and the reactive power is positive. And fifth case is the other extreme, minus pi over 2, where one port is purely capacitive. Okay. R equals 0, reactance negative, and power factor 0, but this time it's leading. Okay. P equals 0, and the reactive power this time is negative. Okay. Now, let's apply these definitions to a simple case. Okay. To get a little bit familiar with them. For instance, if you hear somebody talking about certain load at 10 kilovolt amps at 0.8 power factor, or if you read that in a data sheet, it means the following. Load at 0.8 power factor, comma, leading. This means what? Now we have the power factor, so cosine of the phase difference between voltage and current is 0.8. Okay? So what's the phase? Okay? It could either be, okay, so to determine the sign of that phase, that angle, we have to know whether it's, okay, we're told the sign through this word here, okay, so leading. If it's leading, it means the theta is between minus 90 degrees and 0. If it's lagging, it would have been plus between 0 and plus 90 degrees. Okay. Now also we have here some magnitude, okay, which is 10,000. Now what does this 10,000 correspond to? Does it correspond to the real power? Does it correspond to the reactive power? Or does it correspond to the apparent power? Okay, it's not written here, but that information is hidden in the units. Okay, since the units is volt amps, so this means that the apparent power is 10,000. Okay, if it were in watts, for instance, it would be that the real power is 10,000, and so on. So this means that the apparent power equals 10,000 and cosine theta equals 0.8, and PF is leading. Okay, the power factor is leading, so that means theta is negative, which will produce negative sine theta. Okay, so sine squared theta equals 1 minus cosine squared theta. Okay, so that's 0.36. Okay, now the square of minus 0.6 is 0.36. Square of 0.6 is also 0.36. Is it going to be minus 0.6 or plus 0.6? We look at this word here. Since it's leading, theta is negative, therefore sine of theta is minus 0.6. Okay, sine theta equals minus 3/5. And then the real power, P equals the apparent power times cosine theta, which is 0.8, the power factor, as cosine theta, so that's 8,000. Since we're talking about the real power or active power, the units is watts. Okay, reactive power, Q is the magnitude or the apparent power times sine theta. Sine theta is minus 0.6 because the power factor is leading. So this produces minus 6,000. Since we're talking about reactive power, the unit is VAR. Okay, volt amp reactive. And the corresponding power triangle would be this. Okay, since we have a negative reactive power, we draw the vertical side pointing down, so we have minus 6,000 volt amp reactive for here, and for P we have 8,000 watts, and for hypotenuse we have 10,000 volt amps, and this is the theta. Okay, cosine of which is the power factor.